So could you guys start by, could you just explain what your goal was?
Yes.
Sort of what the project is, and then get into the details of the demo.
So our goal was to build a matrix multiplication accelerator or offloader so that if a CPU wanted to do a series of matrix multiplications, it could just, load up some memory location with values that define the matrix, and then basically let the hardware run, and then, do some useful work potentially in the meantime. And then when the hardware is done, it will say, hey, I'm done, here's your values. And the CPU will come back, grab the values, and then the matrix multiplication will have occurred. And so what we're looking to do is compare specifically a hardware implementation with the software implementation, and see the benefits and the downsides of both of them. And so we ended up making two models. One was a very unrealistic but very fast FPGA implementation, where essentially we had one piece of hardware for every output in the output matrix, or every value in the output matrix. So then we ran out of hardware. Ran into a bunch of problems, but we ended up running out of hardware at a 13 by 13 matrix. With that implementation, it would take 13 cycles to calculate a 13 by 13 matrix multiplication. And it works with anything smaller. It will always take 13 cycles. So it's very fast, but it was based on registers. So the HPS would come and load up registers with values, and then the hardware would read those registers. So you get a 0 cycle latency for reading values, and you can read as many values as you want because there's no limitation on the number of ports. Like every single piece of hardware was hooked up to every register it needed to read from. So there's no bottleneck at all. Then we made a more realistic implementation that used M10K blocks. So then, of course, you run into the problem of you have one read port and one write port on the M10Ks. So instead of having this massively parallel structure like we did in our unrealistic model, we have a more realistic, we have one hardware multiplier that goes through and iterates through the output and calculates each value in the output matrix. So that was the goal of the project. And then, so for high level of the code, so this is the unrealistic model. Essentially, this is all code that just figures out when the multiplier is done. This is code that takes inputs from the HPS. And then this is really the meat of it is here, this generate statement. We've got iterating over, and we're generating however many, which ended up being a 13 by 13 grid of multipliers. And then I was talking about those problems before. So what we ran into was we were trying to use 18-bit numbers. So we were trying to use 18-bit multipliers, which what we thought from lab 2, I believe it was, should have given us whatever it is, 87 times 2 multipliers. 174.
Yeah.
But so when we were doing this, we ran into the problem of every single multiplier we defined, Cordis was trying to use one DSP block. So it was only letting us use 87 multipliers, which isn't that great. That's a 9 by 9 matrix at most. So what Bruce suggested and what we ended up doing was we've got these two instantiations. One is matrix mult and the other is matrix mult logic. And what these are is they're exactly the same thing, except that for their multiplier, matrix mult uses a DSP-based multiplier, and matrix mult logic uses a logic-built multiplier. And so that's what ended up letting us get so many multipliers, because otherwise we would have been limited to a 9 by 9.
And this allowed you to bump up to 13 by 13?
Yep.
Okay.
So obviously, since we're building these multipliers out of logic, we have a decently high utilization of our ALMs. We're using most of our DSP blocks. We just did it simply where when we're iterating through we generated 5 times 13, so that's whatever it said in Quartus, 75 DSP multipliers, and then we generated the rest out of logic. And then so for the actual implementation, they're pretty simple. They're just multiply accumulators. They essentially just take in clock reset, and whether or not they should be running, they take in an 18-bit value for M1, 18-bit value for M2, and they output this 18-bit value. And so what they do is, this is the name of our instantiation of the DSP-based multiplier. So it just takes in the value from M1, the value from M2, it outputs their multiplication. And then we've got this little block down here that basically, if we want to run, then it multiplies and accumulates that value. So that's how we end up with the output value for the matrix. And then, as I mentioned before, the logic one is the exact same code. It's just that its multiplier instantiation is our different instantiation, where we specifically told Quartus, hey, make a multiplier out of hardware instead.
Okay.
So for a realistic one, it's significantly more. Oh, yes.
Just if I could ask a quick question. So that one's totally in parallel, right?
Yes. So every
Okay.
single output is calculated, every single one within 13 cycles. So in
Okay.
13 cycles, you have the output matrix.
And you're using the word unrealistic. Is unrealistic only because you're limited to 13 by 13 or less?
Yeah, and the fact that you need an 18-bit register for every single, you'd need n squared times 3 registers if for your maximum sized matrix. So that grows pretty exponentially, and so that's why we call it unrealistic.
Okay.
Although for computer graphics where you have to do a lot of 4x4s, this would be perfect.
Yes,
That's true.
yeah.
Right. Yeah.
So then for our more realistic, meaning that it's out of M10K blocks, so you've got a lot more of those. So essentially, again, if we start at the top, let's see. This is a hardware timer. Basically, it tells us how many cycles it took for the hardware to multiply and get to the output. This is the same block, essentially, that we saw that takes inputs from the HPS and then gives values back to the HPS. And then, so this is information about reading. So it's how the HPS is able to get values out of the M10Ks. So in the other version, it's very easy to read values out to the HPS because there's no latency. Like, you request a value, it's right there. You can just send it on over to the HPS. Whereas this one, you've got that one cycle. You need to request the value from the N10K, wait a cycle, and then you can return it.
Right.
So this is just some logic that takes care of that. These are all the control signals that allow you to initialize the two M10Ks for M1 and M2. So in the initialize phase, the HPS is allowed to put values into M1 and M2 so that we can actually multiply things that have values, and we can control it from the HPS. And then otherwise, our operation is just that we are reading values out from M1 and M2 and giving those to our multiply accumulator so that it can do that multiply accumulation and then spit out the value in the end. That should be the output value for the given row and column in the output matrix. And then, so the big difference you see here from the other one is that instead of generating a 13 by 13 grid of multipliers here, we're generating several M10K blocks. So we've got M1, M2, and the result M10K blocks. And each one of them can hold up to 128 values. And the way we thought of it was essentially the 128 values are for one single column in your matrix. So then the number you generate of these defines how many columns you have for your multiplier. So we generate, this is a parameter that's currently set to 80. So it can do up to an 80 by 80 multiplication. And that was because we were limited by M10K blocks actually, which kind of surprised us. But with the 128-bit M10Ks and 80 of them times 3, we were running out of M10K blocks. So we have an 80 by 80 matrix that we can use. This is where it generates that. And then this version, we have a single MAC that basically goes through, requests values from M1 and M2, requests an entire row of M1 and an entire column of M2, and then writes that value to the result M10K. And then, so if we go over to Cordis, so the other version took 67 or almost 70% hardware. This one is significantly lower. And then it is using a good amount of our M10K blocks. But the main takeaway is that this one is significantly more lightweight than the other because it's using M10K blocks rather than hardware to actually store all these values. And then Liam, do you want to show the one running?
There are also ways, like just on the M10K blocks, there are probably ways that we can optimize it, right? Because you can store 512 20-bit values in a single block. So if we wanted to optimize it further, there's possible that you could just stuff 2 columns in a single block instead of what we did, which is 1 column per block.
Sure.
So yeah, here I'll load up the code here. So here this is our baseline. This was just on the HPS. This is matrix multiplication using an n-cubed algorithm. So it just goes ahead and initializes a matrix of like size n by n, which is determined by this matrix size parameter here. And then we of course just do the matrix multiplication and print the result. So that was just our baseline to test our result with. And then move the zoom controls. This was the actual one that interfaces with our realistic implementation of the FPGA hardware. So as you can see here, we set up all of the structs to actually get the timing information. That was just for testing. We have all the pointers for the AXI bus where we're actually exchanging values across to the FPGA. And then we have this like control scheme. It's just a 3-bit control pointer that basically tells reset, writing, and then reading the values. So of course we set that to different things according to what we're actually doing. So when we initialize the values, we call this initialize function here. That just goes through, sets the control signals, and then feeds the 32-bit val of the X and Y coordinate, sets the value because we have to serialize it one at a time. And then, it does that n squared many times. And we do that, or actually 2n squared many times because we initialize both matrices. And then there's not much logic for actually computing the multiplication because we're just waiting for the FPGA to actually do that work.
Right.
And then we read out the values also serially. And then we do some timing information. So we did do some cursory tests just to get some interesting tail latency numbers. So we ran 1,000 tests for each size matrix from 20 to 80. So 20, 40, 60, 80. And we did it. So this COM-M is like computing the matrix multiplication on the computer on the HPS. And then this matrix multiply is actually using the FPGA hardware. And what we see here is actually, not necessarily what we had expected. We expected our FPGA implementation to be, at least a little bit faster than the computer. But what we actually see here is because since our FPGA implementation is clocked at 100 megahertz, the HPS has, 10 instructions per every FPGA instruction. So it's likely that, a single multiplication operation in the FPGA, or rather the HPS will not take 10 operations to do the same thing in the FPGA. So that's where we see some of the overhead come from.
Sure.
But some of the interesting statistics that we see from this though is that, the FPGA one is just very predictable. It's the same number of practically the same number of cycles for for each test run. So we did 1,000 runs. We see that, the mean, median, 90, 97, 99th percentile, it's all basically the same. Whereas you see a pretty normal-ish distribution with the actual computer runs as you see the strictly increasing sort of statistics. So that is at least a plus side, is that, the jitter to get the result is significantly reduced in the FPGA implementation.
Does this time include the communication time?
This time does not. This time is purely calculation time. So that was our apples to apples. If we did include, we noticed the high amount of process variability in terms of, printing values. But we do have data. We just have not analyzed the actual setup time in terms of like setting up the matrix in C and then actually sending it across the bus.
So the overall conclusion is that the speeds are about the same, really.
Yeah, they're very comparable, and it's a very promising result. It might not have necessarily been what we had wanted off the bat, but it's promising in the sense that our hardware is relatively simple. So for the amount of time that we we did this in a week, and the amount of hardware that we're actually using on the FPGA is comparatively low. There are ways to optimize this, and we see how it scales. It scales exactly according to an n cubed, best fit curve. And you can see, so here's the FPGA in blue, the median run times for each of the size matrix. You can see that if we were to find a way to either do more things in parallel or to even overclock the FPGA a little bit, there are potential ways that we could just drop this curve below so that it's consistently below the HPS compute times.
Try clocking to 200 megahertz.
Yeah, so we tried clocking to 200 megahertz, and then we were running into problems of just reading out garbage from the FPGA. So I'm not sure if it was failing timing, because even on a run that works, we're failing timing, just based on the timing constraints set up. But basically, yeah, if we tried clocking at a higher clock frequency, we tried two different ways. We tried leaving the part of the code that interfaces with the HPS and the AXI bus to run at 100 megahertz, and then we let the part that actually does the calculations run at 200 megahertz, and we still ran into the problem of getting garbage out. And then we also tried clocking everything in the FPGA at 200 megahertz, and we still also got garbage out. So that is definitely a possibility. And as Liam was saying, if we were to get that higher clock frequency, then this line would drop below. And if it dropped low enough, then we would be consistently faster than the HPS. We just ran into the problems of clock domain crossings and or timing constraints not being met when we increased the clock frequency. So we weren't able to do that. But another plus of this was, as Liam was saying, we used so little hardware, and also we made it extremely parameterizable. So we have an 80 by 128, but if you had an FPGA with more hardware and or you configured your M10Ks in a different way, all you have to do is change a single value in the Verilog, and it will generate however big of a matrix you want. And it takes care of all of the nets, all of the buses, everything within. It will just work if you just increase the one parameter.
And of course, that relates to the maximum size matrix that you could, there's no, if you wanted to do 15 by 15 and you already wrote the hardware for 25 by 25, you can just put that in and see and set everything else to zeros. And because of how the multiplication works, you can just ignore the rest.
Yeah, that is, yeah, we have our maximum size, so it's an 80 by 80 right now, but from software, you can just say, I want to do a 20 by 20, and it will work with the 80 by 80 hardware. So you can do any matrix that's smaller than 80 by 80 right now.
Okay.
And we can run it. Do you want to run it just once in
Sure.
the terminal?
So we've got a couple pre-built things. So this is just, so actually we'll start with a 20 by 20 so you can actually see the results. So this is running on the FPGA. So we print out the result. It's a pretty simple matrix. We're just going through and, increasing by 1 each time when we actually, make the two matrix to multiply. You can see that we're outputting the number of cycles that the FPGA took for calculation, but we're also using just like the built-in timing information and to see, to actually get like real times as opposed to just cycles that the FPGA took. This, of course, is coming off from the AXI bus from the FPGA itself. So there's a counter that we have in hardware, and that's passing it to the C code.
Okay.
And then if we wanted to verify that this is the correct result, you know, our rudimentary C code should be able to produce the right result. We see that the results match, and we see that, again, it takes a little bit less time, at least in terms of calculation here. We see that we took 73 microseconds as opposed to 94 microseconds with the FPGA. Apparently malloc is really quick and freeing is really quick, because we see that the setup time for the FPGA is actually higher than that of the C code. So some interesting tidbits in there.
There's a couple of things occur to me. One is, which we've been talking to all of the groups about, is that an interesting measure is energy use. It takes about the same amount of time to do the calculation on the FPGA, but I'll bet you'll find that the FPGA is using less than a quarter of the power of the HPS.
Yeah,
Right, because you're running at almost 10 times the frequency. So you have
Right.
far more switching going on in the HPS than in the hardware.
Right. And you also have the fetch execute overhead, which you don't have on the
Yeah.
FPGA. And there is a power estimator module in Quartus that will tell you how much your design is using. All you have to do is take your compiled design and run it through the power estimator. It takes like 2 minutes.
Okay. Okay. Yeah, we'll definitely put that in the report.
If you just do a search on power estimation on the main web page, you should find a link to a page that describes how to do this.
Do you know if there's like the Linux LM sensor package on the HPS? I guess we can just check it.
I don't know, but I know that there is no hardware current sensor on this particular FPGA.
Gotcha. So it won't tell you like.
No, but the
Okay.
power estimator will estimate.
Yeah.
The second thing is, we haven't really talked about it very much, but there is a data structure which is intermediate between registers and M10K blocks. It's called MLAB blocks. And they're more granular. You define them in blocks of 20.
Okay, yeah, that's a little bit better.
So you can kind of fit stuff in them better. They're more limited. You've got about 600 M10 MLAB blocks, but in the, if you had another month, you could play around with MLAB blocks. They have different timing constraints also. They're a little faster to read, but all in all, it's impressive that you match the speed, because you say the clock rates are so different.
Yeah. No, I think it's interesting. It's a very promising result. I mean, one being that, we were able to match the result with, comparatively like less amount of hardware. I mean, we worked on this in the past like week and a half or so. We were able to get this work.
Yeah.
And then the second thing being, brain is fried.
Zoink.
I lost it. Oh well.
I think it's a cool result.
It's good.
Yeah,
Yeah,
I mean, it's certainly promising. I mean, oh yeah, that was the second point being, is like if this was truly an accelerator, right? Like, it's not necessarily like it's not a bad thing that it takes just as much time, right? Like, you don't necessarily expect it to be the utmost fast. It's just the idea that you can offload computation, and then those cycles can be spent doing something meaningful with the CPU.
Right. So you have effectively doubled the speed of the HPS in that case.
Right.
Yeah. Like you could do 2 multiplications at about the same time that you could do 1.
Right.
If you can offload 1 and calculate 1 yourself.
Or
You want to run the 80 by 80?
Sure. Yeah.
They
It's
are
just kind of a
impressively
method that
fast. They
we-
still only take low milliseconds.
So there's the 80 by 80, and it's
Yikes.
stuff on this. But we
Yeah,
can
it took-
see 500,000 cycles. So at 100 megahertz, that's just over 5 milliseconds.
Uh-huh.
So impressively. And then, of course, if we run it on the HPS alone, we don't get cycle data because we didn't put that in the code, but we see that it took about 4.1 milliseconds.
Are you running on the HPS in floating point or fixed point?
This is all integer. So just like our FPGA
So
accelerator.
it's a fair comparison then.
Yeah.
The reason
Yeah.
I'm saying that is that the integer is
You do twice,
dual
right?
issue.
Full pipeline.
It's dual issue in integer. So you actually get twice the cycles that you think
Sure.
you're getting.
Mhm.
And the floating point unit is single issue.
So we could,
Right.
could probably beat the pants off the HPS if we did floating point. If it's would be half as fast on the HPS if we were doing.
It should be very close to half as fast. Yeah.
That would be
That wouldn't be
interesting.
too bad either. You just have to change the number format and then change the multipliers, and that would be it.
You might want to just mess with it and see what it is. But again, you might have other priorities like sleeping or writing this up by Monday. Or
Yeah, and writing up our MN reports.